All right, everyone. So I think we're going to go ahead and start. I will just introduce our speaker for today. Professor Notomista is an assistant professor and the Verma Family Professor in Robotics in the Department of ECE at the University of Waterloo. Prior to joining the University of Waterloo, he was a postdoctoral researcher at CNRS in Rennes, France. He received the PhD degree in robotics from the Georgia Institute of Technology. He is a Fulbright scholar and was the recipient of the Alumni Small Grant and the IEEE RSO Best Paper Award. His main research interests lie at the intersection of design and control of robotic systems for long-duration autonomy with applications to environmental monitoring. So without further ado, the floor is yours, Professor.
Thank you very much for a very kind introduction. And in this presentation, I'm very excited to tell you about learning to execute prioritized tasks of robotic tasks. Thank you again for the invitation. This is what do AI seminar series. Right, the motivation to this work comes from my interest in long-duration robot autonomy. So this is a discipline that studies robots deployed over long time horizons and has a lot of different applications, which we can see represented on these slides. Starting from the leftmost, we see a Mars rover opportunity, actually one of the most successful ones, which broke all the records of longevity by surviving on the surface of Mars until actually a dust storm covered the entire planet, so spread on the entire planet, and covered the sun and prevented the sunlight to actually reach the solar panels. And that was the end. There was nothing else that could be done to recover it. The second feature is a post-earthquake scenario where teams of robots, here we see two ground robots and one aerial, one copter in front of the traffic sign, which are tasked to explore this kind of new environment after a disaster in a way, and figure out what are the important features in this environment to be able eventually to find people in this environment. The third picture shows two robots, again, one ground, one aerial, deployed in an agricultural field. And agricultural robotics actually is one of the most prominent applications of long-duration autonomy, since it's a market that has grown and is growing faster than all the others. And here robots are deployed again over very long time horizons to figure out the state of growth and state of health of plantations, which are phenomena that take place over time horizons of weeks, months. And this is the time span that we want the robots to be actually deployed and successfully operational in. The last picture shows a couple of autonomous surface vehicles. So again, we have teams of robots here deployed on the surface of the ocean with the objective of collecting data about the ocean in terms of the salinity or the content of CO2 or even the air quality, right, around air temperature and air humidity around specific regions on the surface of the ocean. And so in all these applications, it is clear that, well, except for the first one yet, we have teams of robots, first of all, deployed over very long time horizons, and these teams are actually heterogeneous in the sense that they are made up of robotic platforms which are very different from each other. Ground aerial is one example, but also equipped with different sensors and capable of executing different tasks. And so the application that I'm interested in, motivated by these scenarios, is that of the energy-aware and resilient environmental monitoring for climate change ecological studies in particular, using heterogeneous multi-robot teams. The motivation, I think, is kind of clear, but we will oh, maybe this mic is on? Oh, yeah, I believe so. Thanks for the feedback. The motivation is pretty clear, but we will actually exploit this heterogeneity, right, for long-term environmental monitoring to achieve energy-aware and resilient operations. Another thing that is clear, actually, from these applications, particularly the first one, for example, is that we need a synergistic combination of the design of a robotic platform as well as the control to achieve long-term autonomy. Just the design alone is it's not capable of letting robots survive forever, and the control alike. So with these premises in this presentation, I'll first of all introduce what we call the constraint-based control paradigm, which is in a way a paradigm that is amenable for long duration autonomy. We'll see how energy awareness and resilience are two properties of robotic systems that can be very suitably encoded in this constraint-based control paradigm. And then we'll put everything together and show how long duration tasks can be actually learned, combined, prioritized, and executed by teams of robots. So let's start with the constraint-based control paradigm. The motivation comes from ecology. On the top left here in these slides, we see a sloth, a three-toed sloth, as it is called, which are animals extremely interesting in the sense that they are so obviously the result of an optimization in nature. Namely, their size is large enough to be able to host a digestive system capable of digesting leaves that they eat every time that they are awake. Not much, but every time that they are awake. And they are small enough, actually, to be able to live on trees and not fall out of the sky and be eaten by jaguars that are passing basically their lives waiting for these moments to emerge. So ecological studies have actually shown that the behaviors and even these properties of these animals are determined by the so-called ecological constraints. So whatever surrounds the animals, and not by objectives, right? So it's not that the sloth was trying to do or to aim at something interesting and then it ended up like this, but it was constrained by the environment. In the same way, you believe that you are you wanted to see this talk about learning robotic tasks, but actually you were constrained by someone to come here or to join the Zoom meeting. From an engineering perspective, going from a slot top left to a slot bottom left, we see that there are advantages of constraints over objectives in the design of robot controllers. And this is highlighted in this green box. So while there is no right way of combining objectives, people have spent their lives like trying to multiply them or compose them in different ways. There basically exists only one way of combining constraints, which means enforcing them all. On the left, we see here the first example of a slot bot deployed in the Atlanta Botanical Garden in 2021, alone in the middle of the pandemic. And survived until, actually, what did I say? 2020, and survived until 2021, collecting data about the environment in the botanical garden. All right, from a mathematical point of view, we could think of defining a constraint-based control paradigm to execute one task as follows. So here we are just asking to execute a task encoded by the function ctask. There is a function of x, the state of our robot, and u, the control effort spent by our robot, less than or equal to 0. That is somehow meaning the execution of the task. And the other thing we need to do to execute this task is basically be as lazy as possible, minimizing the control effort, hence the slot. The optimization variable in this case is the energy spent. So that is the minimum energy in a way paradigm. And as said, that's the function ctask, that is a function of the state x and the control effort u, is somehow encoding this task. For example, we will see the multi-robot environmental monitoring. In one slide, how do we encode task as a function ctask less than or equal to 0? The key is in this drawing, which shows two examples of two sets S in the state space of our robot, defined as the 0 super level set of the function of a function h. Namely, S is the axis in Rn where h of x is greater than or equal to 0. And there are two properties which are particularly interesting in these tasks.
or for this set. One is set stability here, which if you are working control, that's your obsession, and you should know what it means. Basically, if we start somewhere at xt0 at time t0, we would like to approach this set eventually, asymptotically. The other one is set invariance, the one shown on the left, where we basically see a trajectory of the state that originates at xt0 within the set and remains confined within the set. So if that happens, the set is invariant. If the trajectory approaches the set from outside, the set is stable, or in this case, asymptotically stable. So turning state spaces into just numbers, which is the key for Lyapunov functions and control Lyapunov functions. What we see on this slide is actually the same picture, right, showing the trajectory of the state originating in xt0 when it starts from outside the set here, and h0 is less than or equal to 0, or inside the set where h0 is positive. So what this picture means is that if we would like a set to be stable, we just need to ensure that the function h, which in a way defines the set, approaches zero as time goes to infinity, which means the state is going to get closer and closer. And that's a Lyapunov function, basically. If we would like the set to be invariant, what we need is that this function h has to remain positive for all times. If it is positive, the state is inside the set by its definition. So as long as h is positive, x is in the set. So we turn something that is extremely difficult to make. How do we make the set, a state x in Rn to remain within the set or to approach a set? By picking what? A controller in Rm, m numbers, something which is in a way very difficult. So something very simple, because we reduce it to one dimension, right? We just need to keep the value of a function positive or to make it approach 0. This is the pictorial view of things. Mathematically, if we are given a robot model, so how the input and the state influence the motion of the robot, x dot is equal to f of x plus g of x times u. This is a special case of a nonlinear system called control affine, where u, the control variable, is affine. Well, x dot is an affine function of u, which is very common in mechanical systems, in particular in robots. And we consider tasks that can be executed by making a set asymptotically stable or forward invariant. And we will see examples of this, and we will be convinced why this makes sense in a way. So this is achieved by enforcing this constraint. So now we have an expression for C task, where these strange symbols are the Lie derivative of the function h in the direction of the vector field f, simply partial h partial x times f. If we are in Euclidean space, this is just as nomenclature to sound fancy. This is the same LGH times u minus this alpha of h of x, where alpha here is a so-called class K function, which is basically a continuous function, monotonical increase in passing through the origin. I won't go into the details of this, but the idea is that if this constraint is satisfied and h starts positive, it will remain positive for all times. If this constraint is satisfied and h starts negative, then h will become 0 at asymptotically. And this h is a so-called control barrier function. So with this in mind, if we have this constraint-based control paradigm again for m tasks, each of which is represented by this function, then we can just stack constraint C task I through C task M for m tasks into this optimization and solve for the control input U to give to the robot. C task 1, in the example of multi-robot environmental monitoring, can encode energy awareness. C task 2, data collection, which is something useful for environmental monitoring. C task 3 can be data processing, in a way, if we're building a model, right, of the environment, we might actually need to perform some computation. And this tree can be, in a way, encoded in this way, as set invariance or set stability. Let's see the first example, energy awareness. So if you didn't believe that energy awareness could be actually encoded as a set invariance or stability constraint, this is how it's done. So the H, E sub E, which is a function of the state, and the energy E of the robot can be defined as a control barrier function like this, right? E minus a minimum threshold, a lower bound, beyond which we don't want the robot energy to fall, minus this term rho of P of X minus PC. This is an upper bound on the energy required by the robot to reach a charging station. The picture is if your bed is on the 10th floor of an apartment building, right, and you're very tired, then you need to make sure that you have enough energy to get to the 10th floor before falling asleep. Otherwise, you will not get to your recharging station in a way. Here, Px is the position of this charging station, and sorry, Pc is the position of the charging station. P of X is the location of the robot in the environment. And we can be convinced at this point that if HE is positive, then the robot will reach the charging station before its energy goes below E min. So the only thing we need to do is to keep E min positive, which means set invariance. All right, let's go back to the M tasks. In this case, N robots that need to execute our multi-robot environmental monitoring. Here we have X and U, which are the stacks of the states and inputs, respectively, of the N robots. These constraints, for what we have said in the previous slides, can be substituted by this, right, which is basically the same constraint that we saw before for each of the robots. And this is a proxy for tasks that can be executed in this way. If we want this task execution to be energy aware, then we basically stack the energy constraint that says for each of the robots, the energy has to remain above a lower bound. And that's constraint based with energy constraints. How does that look? This is an example of a so-called coverage control task, where we see 6 robots here, 1, 2, 3, 4, 5, 6, that are tasked with spreading over the environment. And this is some proxy for monitoring the environment, subject to their energy constraints. So there is an energy in the battery of this robot that, in this case, is simulated because the charging stations are actually outside this field of view. But the simulated charging stations are here on the left, these disks. Their energy has to remain above a certain bound, and they also need to avoid obstacles in this case. So this is another set invariance constraint that can be stacked into the system. So what is done, how this is done is basically by each of the robots driving towards the centroid of its Voronoi cell. If you're familiar with multi-agent coordination, this is a pretty standard coverage control task. And as basically as simple as drive to the centroid of your cell, period. At the same time, they need to avoid obstacles. So these robots that are simply there to disturb. And they need to run to charge. As said, in this case, simulated, also to have faster charging and discharging cycles when their energy is falling down. So all these, which is kind of complex, is also 4x, is actually the laziest possible behavior for these robots. They are minimizing the energy point-wise in time to be able to cover the environment, avoid obstacles, and prevent that their energy goes down. So this was everything for energy awareness. Now let's talk about resilience. Should we do questions at the end or through the? Let's do it at the end. Let's do it at the end. yeah, the second thing that we're interested in when we deploy robots for long time horizons is actually resilience. Right? So energy awareness is one, in the sense that we obviously don't want the robots to discharge, right, their batteries. Resilience is the other thing. The definition of resilience is actually not in a way final, right? So in particular in robotics, people have started to think about resilience only recently. But we can talk about resilience as the ability of a system to recover from a failure that happened. Now, the key is that this can be done either by altering its behavior or its objective. This is, I mean, should convince you that it's different from robustness and is different from adaptivity, which are two things which share somehow similar notes, but they're not the same. Right? We want to be able to structurally change the behavior of the robot, right? In order, the robots in this case, for them to be resilient. Why is there this so-called Mercedes frame? Not because I particularly like the Mercedes, but because we're going to use frame theory to encode and enforce resilience of multi-robot systems when they are controlled using this constraint-driven control paradigm that we saw. For that, there are the two most boring slides of this presentation. One is the definition of a so-called tight normalized frame. What is a frame? If you are in signal processing, that is you'll be familiar with this because they're actually a robust basis for, in this case, a Hilbert space. Basically, we have a set of vectors, just like the basis they are able to represent, right? Every vector in this Hilbert space, but actually they're able to do it in a redundant way. There are more than required. In particular, in this case, we have n dimensions of this Hilbert space, and we have d vectors, di 1 to d. The key for a frame is that basically the norm of y, any vector in this Hilbert space, has to be somehow represented by the sum of the inner products with all the vectors in this set. This looks very similar to what a basis does, right? In fact, a frame is tight if the two A and B's are the same, right? So there is an A that is greater than or equal to 0, which means that we are able to represent any vector y as the expansion, right, of this vector in the directions of the vectors vi's. Moreover, it is normalized if all the vi's are have norm 1. You can think of a basis and just a robust version of that because we have multiple components, right, than the minimum required. Why is this interesting in all this? Well, because there was a recent frame characterization for the tight normalized frames, which reads as follows. If we consider this potential, fp is a function that maps from the vector on the sphere, right? The d-dimensional vector on the sphere in this n-dimensional Hilbert space to a positive number, which is given by the sum of the inner products between all pairs of these vectors. And what do we do with this? Well, first of all, every local minimizer of this frame potential is a global minimizer, which is extremely good when you think of optimization, which means if you find any minimizer, you find the best. If n is greater than or equal to d, right, then the minimum value is whatever, and the minimizers are the finite normalized tight frames. So basically, we can minimize this potential, frame potential, and find the finite normalized tight frames. What is the connection with what we are doing here? Let's go back to the M tasks and robots of constraint optimization, where we have these constraint functions here. If we have actuation disturbance to the robots, so U is somehow not possible to be executed as it is. If we have a computation disturbance, some of the modules breaks, or we have not enough time to figure out what the optimal U is, Or even if we have communication disturbance, because if the tasks are collaborative between different robots, we might need information from other robots to compute our control input. So communication disturbance can actually make the computation worse, right? Not optimal in a way. Then there is a mismatch between the optimal multi-robot behavior and whatever is executed. This mismatch is quantified by this delta, right? Which is in this case an expectation. And we can show that this mismatch delta is minimized when, look at that, this LGH, fancy Lie derivative, is a finite normalized type frame. So we basically have to make the robotic system resilient to these disturbances in a way. We just need to make LGHI a finite normalized type frame. But now we know how to do that, right? We just use a frame potential. And this ugly looking equation is exactly the same that we saw before, but specialized for the case of LGHs instead of VIs. Plus there is some terms to make it normalized. In fact, the proposition is that if, ALGHI is the set of this vector is a minimizer of that frame potential, if and only if it is a finite normalized type frame. I hope you survived to this number of equation thrown like this. There is a couple more, one more actually. So starting from the M task and robot plus the energy constraints as we had before, we can stack yet another constraint, which we can call the resilience constraint, whose objective is to make FPR, is to minimize FPR. So what are we saying here? Robots should execute their task. They should do that provided that the energy doesn't fall below a minimum threshold. And while doing that, they should also somehow rearrange themselves in such a way that if a disturbance occurs, then the mismatch between optimal and executed behavior is minimized. This is what happens as a result of the execution of the solution of this optimization. Now, simulation results. We have 6 robots, 2 tasks. The 2 tasks are the coverage control that we saw before, spread over the environment. A formation control, which means assemble a specific geometric shape, which is a proxy for assemble a communication network, for example, between a base and a target station. And then we have 6 charging stations as before. Now you can see them more clearly in the simulation. And we have 2 failures. So we have one robot that breaks down at 180 seconds, that is a third of the simulation. And then another robot breaks at time 240. Breaks means that their U is equal to 0. So it's not the U star, whatever solution of the optimization, but it's just 0. The motors fail. So qualitatively, without and with the resilience constraint, this is how the behavior looks. So what this motion is, let me actually stop. So at this stage, here and here, the robots are actually executing both tasks, coverage plus this formation. They assemble roughly like the same shape and the same kind of distribution in the environment. At some point, some of these robots go to charge, and one of the robots will become gray, in this case, here, which means has failed and has stopped moving. So the others, while performing their task, actually rearrange themselves. And as you can see at the end, they achieve different end configurations. Now, pictorially, can you see that one was resilient and one was not? Obviously not. Quantitatively, we see that, first of all, the energy control worked, right? So we have that all the robots were actually able to keep their energy, these colored lines, above the E-min, except for one, which is actually the one that failed. So it failed away from a charging station and was not able to recover anymore. From a resilience perspective, we see here, so here is a quantitative measure of resilience. We see that the quality of execution of the task, which is inversely proportional to the value of the functions plotted here, is actually better, it's higher, when we have resilience constraints, right? So the red one, so the green one is as if nothing happens, so the robots do not break. So it's the best you can actually ever do. The red one, right? Oh, sorry, what did I say? The blue one, which is the with resilient constraints, is lower than the red one. Here is actually pretty close to the optimum. Here is slightly lower than the without resilience constraint, but anyway, it's better. And these two are basically for the quality of coverage and the quality of formation, how well we were executing the two tasks. All right, so now comes actually the real question, which is what kind of tasks, right? We could do. I showed you coverage, formation, energy, awareness, sure, but there are many more tasks that robots can execute. So this we will, in a way, show what tasks can be executed by starting from where we began, right? The constraint-based execution for n tasks. Doesn't matter how many robots for now. Let's say we have n tasks. Is feasibility, right, an issue? Like, any one of you being concerned with feasibility of this? We have a lot of constraints in this optimization. First thing that you should think is, well, this is gonna break at some point, right? Some of the constraints are going to be actually not compatible to each other. Or we can put slack variables, basically just relax the constraint up to the point that you can also satisfy them all. And here delta 1 to delta n are these slack variables, and kappa times the norm of delta, which is the stack of all the slack, is just weighing how much we sacrifice the tasks, deltas, with respect to how much we want to execute them, how well we want to execute them. Fine. Question one is, yeah, what kind of tasks can we execute using this paradigm, as I was saying before? C task, sure, it's kind of expressive, but what else? And question two is actually slack. What do we do with slacks? We're basically saying, yeah, C task less than 0 is the execution of the task. C task less than delta, and who knows what delta is, comes from the optimization, means that how are you going to execute this task? How well? If you relax them all, this is actually saying, I don't care about all executing tasks, and good enough is good enough, right? This is what this is saying. So let's solve these two problems by looking at this block diagram, where the connections between optimal control and so-called value functions, between value functions and Lyapunov functions, and between Lyapunov functions and prioritized execution of tasks is highlighted. Now, the connection between optimal control and value functions is very old. I'm not going to discuss it. The connection between value functions and Lyapunov functions is much younger and is actually interesting for what we are concerned about in terms of the kind of tasks that can be executed. All right, so we have this parallel between an optimal control problem, where the objective is to minimize, to optimize for a function, input function u, this cost, right, which is the integral from current time till the end of time of some function of the state as well as the input. So here we're saying, I don't know, we want to get to a point in the state space while minimizing the energy to go there. Fine. Subject to the dynamics of the robot. So x dot is equal to f of x plus g of x times u as before. And associated with this optimal control problem, there is a value function, j star, which is a map from the state space to the reals, and basically tells us how much we are left until the execution of this task, right? So this is, in a way, it's going to tell us how much cost we are left, right, to pay until the end. On the right, we see the something very similar to what we saw before using control barrier functions, but with control Lyapunov functions, which are functions, again, from the state space to the reals. And here we see an optimization problem where we are asking to minimize the control input, U, subject to this inequality constraint with various functions like sigma in it. Now, the connection between these two is as follows. The two problems are equivalent, have equivalent solutions for an appropriate choice of this function sigma. And the control Lyapunov function V that shows up in the constraint here is actually the value function J star for that optimal control problem. Where are we going with this? We have two things: optimal control on the left, optimization on the right. If the two things are equivalent, we can execute anything that can be encoded as an optimal control problem using this constraint-based control paradigm. And the question is, what can be encoded as an optimal control problem? Well, anything that can be solved using the reinforcement learning paradigm. Now, reinforcement learning is just an algorithm to approximate dynamic programming. And the green box transforms into, we can execute any task that can be learned using the reinforcement learning paradigm, using the constraint-based control. This is the idea. In math, it looks like this. So we take the J star tilde, that's the approximation of the value function, J star, for each of the tasks that we have learned using a reinforcement learning paradigm, deep reinforcement learning, where this Ji star is a neural network. And we stuck it in there. Computationally, this is extremely easy. LF, LGs of the J stars are actually involving the gradients of J star, which back propagating through the network are actually easily computable. Lambda and sigma are appropriately defined functions which can be defined offline and make the solution of these equivalent to the solution of the optimal control problem. So here is the answer to Q1. Anything that can be learned using reinforcement learning can be executed using the constraint-based control paradigm. And we have multiple of them, multiple tasks. And so in the final part of this talk, we'll answer the second question, which is, what do we do with those slack, right? Slack variables? Those are actually endangering or worsening the execution of our tasks. And this can actually be understood by looking at the connection between Lyapunov functions and the prioritized execution in the context of this optimization-based control. Yeah. So we have this same optimization that we started from before. We had the slack variables that we introduced somehow to make the optimization problem feasible. We can stack yet another constraint that is called k delta greater than or equal to 0, where k is a matrix which enforces the so-called relative priorities between the tasks. In this way, so k that, let's say the first row of k delta greater than or equal to 0 would read as delta I less than or equal to delta j if we want task I to have higher priority than task j. And this is what happens. Now, if we take this whole optimization program, we put it in feedback with the robot x star is equal to f of x plus g of x u star, what we're going to get is a behavior, but who knows what happens? Well, we try to figure it out with this convergence proof in terms of the state in which the robots end up, which tells us how the different tasks are being executed as a function of the kappa, which weighs the relaxation variables, and the big K, which specifies the stack of tasks. So what do we do with this optimization program? Let's try to do the environmental monitoring problem. So we'll tackle it from an active sensing perspective, which means we are basically optimizing the trajectory of the robots to collect as much information as possible. All right, the robot state dynamics are as before, so control are fine. We have energy dynamics. These are the ones used in the fewest works. Basically tell us that the E dot depends on some parameter A and C of the battery. These are chemical parameters. And beta of U max is a function that basically tells us that the more we move, the more energy we spend. We have an environmental field dynamics. So this means that we have a model for whatever we want to explore in the environment. It could be, for example, the distribution of temperature, luminosity, the gas evolution within an environment. Moves according to that dynamics, where theta are the parameters of this model. For example, the source of a gas, right, leak, and the rate of expansion. So these are the parameters that we are trying to somehow estimate. And then we have a measurement model, which means how the robots actually take measurements Y of the temperature, luminosity, gas density, or whatever. Okay, so the objective, as I was saying before, is to optimize trajectories of state x of t for the robots to collect measurements Y based on that model in such a way that the field parameters theta are estimated by collecting as much information as possible, at the same time while never depleting the energy. So this is the structure. How do we execute the monitoring using multiple robots? First of all, if we have multiple robots, they need to coordinate to each other. Otherwise, it's kind of pointless to have multiple robots. You might as well have one that goes around the environment alone for maybe more time, but as effectively. The second, if they are coordinating, is how do we enforce this kind of information exchange, right, between these robots? And you can imagine that this is useful for estimating something in the environment. And then there is a technical problem, relatively minor. Basically, this approach that was developed for environmental monitoring as casted as a trajectory optimization requires the system to be so-called differentially flat, which is a property of nonlinear systems, which is actually very, very useful when you deal with trajectory, so planning and control. And this is not necessarily differentially flat. So the idea is to use reinforcement learning to learn the value function that corresponds to the multi-robot environmental monitoring task. To learn something using reinforcement learning, we need a reward for the robots to keep moving and do something useful afterwards. And this reward, in this case, has been defined using the so-called constructability gradient, which is a control theoretic measure of the information collected. So we start from control theory, we figure out what is this information collected along a trajectory of the state of the robots, and then define the reward as the trace squared is basically a norm of this, how the extent of the information, the amount of information. So what we saw before becomes optimization. What we saw before simply becomes minimized for each of the robots. Your control effort UIs, the deltas, in this case only one, relaxing the environmental monitoring task, while keeping enough energy in the battery. That's the one that we don't want to relax. We want to be able to actually stay alive, operational. So when each of the robots executes the solution of this optimization, these are the resulting trajectories. We see these kind of leaves, right, for colored leaves for each of the robots, which represent trajectory that go back and forth from 6 charging stations, which are arranged in the environment here. Not to deplete their battery. In fact, here we can see the evolution of the energy in their batteries. And at the same time, they are actually collecting data of something in the environment. In particular, we simulate a gas expanding in the environment, and we are interested in finding out its source location which is given by theta1 and theta2, the first two parameters, and then the rate of expansion, which is theta3 and theta4, given by theta3 and theta4. And so we can see that after basically very few iterations, these are, 5,000, 10,000, very few iterations, the robots are actually able to reconstruct the correct parameters of the environmental field. This is, by the way, a snapshot of one of the robots estimates, because each of the robots is actually doing its own. And so you can query any of the robots in the environment to say, wait, where is the source? Right? Where is the gas source? Okay, so in conclusions, briefly, we introduced the constraint-based control paradigm, and we show that this is an effective way for particularly the coordination of multi-robot systems when there are long-term operation constraints. We show how energy awareness and resilience, which are two properties amenable for long-duration autonomy, can be encoded. And we've shown also how to execute tasks over long-term, which are learned using the reinforcement learning paradigm. And with that, I'd like to thank you very much for your attention and open to questions.
Yeah, I think there might be possibly a few questions online. And so, yeah, I think Gary, if you want to sort of unmute and go ahead, or if you want to put your question in chat, whatever works. Oh wait, I don't know if I'm able to be heard on that mic, or if I should unmute it.
Oh.
Yeah, so yeah, we can take questions from the chat if anybody has questions regarding the work. Or yeah, I can probably start then in that case. So with regards to this sort of the proof that you had regarding, I guess, convergence, are you able to account for maybe trade-offs between like over time, if you have like better estimates, maybe you have like a data collection task, over time you sort of need to collect less and less data based on that. Does the convergence proof hold if you were to maybe adapt those values in that case to account for that? Or is it just that once you include like reinforcement learning, you're able to sort of leverage exploitation trade-off work?
Okay, yeah, that's a very interesting question. In this proof, we have constant JI star, so constant learned value functions. Now that I'm thinking of the proof, I would say you can, which means, right, by the way, that once you know how to execute the task, this is going to tell you how they're going to be executed based on the priorities that you give. I'm thinking of the proof, maybe if you have some convergence guarantees on the single, right, the approximations of the value function, then you might be able to show that actually while learning, you might, you might also converge to something useful.
That makes sense. And I guess in that case, like the harder question would be, what if you're dealing with maybe a task that's sort of adaptive? In that case, where the function is sort of changing over time, and then you have spurts where, maybe you don't want to collect more data, and then other cases where you notice there's a change and it doesn't match up with the function that you've learned, you might want to collect more data in that case. I guess that might be maybe a more complex scenario where that proof would break down.
Maybe, yeah, in the sense that if the data collection is one of the tasks, then sure, you can analyze it. If it is not one of the tasks, then you cannot analyze it in this way. Yeah. But that's an interesting problem to solve, right? In a way that you are on your vehicle, let's say connected vehicles, and there is an accident at some point. You want to coordinate this kind of platoon. Then something breaks down, right? And you need to relearn how to adapt, right? To in a way that you adapt to this disturbance in a way.
So again, if there are any questions that you guys might have in the chat or from the audience here, if you might have any questions regarding the talk, feel free to unmute if you'd like.
Whatever question is, what are manipulators in all this? That's a good question. We have something very similar to the convergence proof. What is that? Very similar to this, where you actually have manipulators executing different tasks with different priorities, using this optimization. And so, again, the idea is how well you're gonna and there is an apple that if it falls, who cares? Then you might actually encode these priorities in the execution of this task, not making the glass fall and not making the apple fall with two different places in the stack.
And for this sort of convergence proof, the functions that you have, you sort of mentioned, I guess you could compute them offline. Like, what do they depend on? Do they depend on just the task specification itself, or also the dynamics of the system that you're dealing with?
Oh yeah, that's an interesting question. No, just a task, because then this task, if it is executed in this way, well, potentially formally could be executed by any robot, right, with any dynamics. And in practice, this is not true, because these constraints are built based on the knowledge of the dynamics. If you change the dynamics, then the constraints might not make sense. Yeah.
And so those functions, they're not necessarily identified per se. They're sort of just defined by the task that you specify for the bot itself.
Yeah. What is Barry doing with this?
Yeah, I don't
hand
know.
raised?
I think Barry might have had his hand raised from the start of the talk. So I don't know if he has a question or not.
No, that was just for the echo thing, sorry.
Question in there.
Sorry. Muted.
Question from the room. You mean what type of algorithm? Yeah, sure. Yeah, this was the classic value iteration. Yeah, value iteration algorithm. Because we are interested in getting the value function, and we don't care about anything else. We don't care about the optimal policy or anything. So we care about an approximation of the value function. So that works. Actually, other algorithms also give you an approximation of the value function. So if you learn it using different algorithms, you might still use these, as long as you have a model for the value function. Yeah, they don't have the trajectories. So those are to be optimized. Yeah. Based on the so in reinforcement learning, what you would do is you say, okay, I want to collect as much information as possible. So there is a training process where they go around and figure out what is the best, in a way, action to take for each state. This is, in this case, is done in basically subsequent steps. You first learn the value function, and then you figure out the optimal action to take by solving this optimization. So at each point in time, there is no trajectory information in this. The trajectory is computed in the reward, so at training stage, in the constructability Gramian. Yeah. Yeah, based on their state, their X.
Yeah, I guess I have maybe just one last question, because we do have a little bit of time. But I think in one of your slides, you talked about estimation of environmental parameters. Were you able to sort of empirically test how much data would be required before you were able to converge to true parameters? And I'm assuming that the parameters themselves are sort of informed by maybe physics-based dynamics models to know what you have, or do you just have maybe a set of parameters and maybe you have some of them converging to one mode and then another set converging to another mode or something like that?
You mean the parameter of the environment?
Yes.
Ah,
And you're asking how many data points you need to for them to converge. Okay. So first of all, yes, in this case, the parameters were informed by the physics. Yeah, because they were in particular the source and the expansion rates of this gas. In general, we didn't compare with the different model for the environment, whether this would take longer, right? Just because the parameters are not defined using physics. I have no idea whether this is anything is going to change. A related interesting question to that is that what if you're doing the trajectory optimization or actually the environmental monitoring by estimating the different things separately, right, as separate tasks, would learning the tasks separately, right, and then combining in this way require less data? This is kind of interesting. Right?
But yeah, I think if there are no further questions, then we would just thank our speaker again for the brilliant talk, doing great work in intersections between control and AI. And thank you all for attending the talk as well.
Thank you very much.